Welcome to this explainer. Every single day, millions of us step onto trains, trusting our lives to a system we can't even see. But behind the scenes, railway signaling is acting as this incredible hidden brain. It systematically manages every single movement so that trains get from A to B with the absolute minimum risk of human error, all while maximizing the capacity of the tracks. It's truly a brilliant piece of engineering, and today we're going to dig into exactly how it works.
So here is our agenda for today. We'll be looking at the physics of trains, enter the interlocking, setting the safe route, the green light, holding and releasing routes, and finally, the fail-safe. Let's get into it.
Section 1. The physics of trains. We absolutely have to start here, because this fundamental physical reality is what dictates all railway control engineering. It brings up a pretty straightforward question. Why can't a train driver just look out the window, spot a train stopped on the tracks ahead, and just hit the brakes? Well, the answer to that sets up a high-stakes environment where any reliance on human eyesight could literally be catastrophic. Think about it like this. When you're driving a car and an obstacle pops up, you swerve, or you slam on the brakes and stop in a reasonably short distance. But trains, they are strictly guided by the physical track. The driver literally cannot steer. On top of that, a heavy train moving at top speed has a massive amount of momentum, meaning its stopping distance is huge. By the time a driver physically sees something on the tracks, it's way too late to stop. So, trains absolutely require advanced warning and extremely careful controlled routing.
Which leads us perfectly into Section 2, enter the interlocking swatch.
To solve this massive physics problem, engineers built the ultimate safety layer. The interlocking is essentially the core brain of the railway. It makes the states of different functions mutually dependent. What that actually means in plain English is that it mathematically prevents two objects from ever occupying the same space. It's a strict system of rules, like if signal A is green, then signal B absolutely must be red, and track point C must be locked. It completely removes human guesswork and uses pure logic to prevent crashes and derailments. Now, what's really wild is that before computers, this logic was entirely physical. Huge steel bars and massive mechanical lever frames literally prevented a signaler from pulling a lever that would cause a crash. If you tried to set a conflicting route, the metal mechanism just wouldn't budge. Pure mechanical genius. Today, of course, the system is mostly digital, but the stakes are exactly the same. Modern interlockings operate at SIL 4, that's Safety Integrity Level 4. In the industrial world, that is the highest possible safety standard. The chance of an unsafe failure is vanishingly small, and even if something does glitch or the power goes out, the system is designed to fail safe. It'll automatically drop all signals to red, stopping every train on the network. Okay, Section 3, setting the safe route. Let's see how this all comes together when a train actually needs to move across a busy network. The whole process kicks off when a signaler, or maybe an automated traffic management system, sits at a modern control center and requests a route. But remember, it's just a request. The signaler doesn't directly control the lights or the track. That request goes straight to the SIL 4 interlocking brain. The interlocking then springs to life, acting as the ultimate gatekeeper. It rapidly executes 3 chronological steps to guarantee safety before that train moves an inch. Step 1 is route setting. The interlocking meticulously runs its checks. Is every single section of the required track totally clear? Does this new request conflict with any other route that's already been authorized? Is there any risk of 2 trains ending up face-to-face? If any of these checks fail, the interlocking just flat out rejects the request. Safety first, always. If the route is clear, we hit step 2, point locking. The track points, those are the moving pieces of rail that guide a train from one line to another, have to be perfectly aligned. The interlocking moves them into position, but then it physically locks them tight and electronically verifies that they are locked. This guarantees the tracks won't shift even a millimeter while a multi-ton train is rolling over them. Moving right along to Section 4, the green light. This is the third and final step of the setup, authorization. Only when the interlocking has mathematically proven, without a shadow of a doubt, that the path is secure, will it allow the entrance signal to change to green. Or, on modern lines, it beams a digital movement authority straight into the driver's cab. Either way, the driver finally gets the green light, knowing the invisible brain has secured the road ahead. Section 5. Holding and releasing routes. Now, you might think the job is done once the train gets moving, right? Not even close. The moment that train passes the green signal, the system immediately kicks into route holding. This means everything ahead of the train stays absolutely frozen. Points remain locked, and no one can accidentally set a conflicting route. It's like the train gets its own personal, impenetrable force field, moving along with it. Let's watch how this sequence plays out. The train passes the entrance signal. Instantly, the interlocking drops that signal back to red to stop anyone from tailgating. The route stays securely locked ahead. But, to keep things efficient, the system uses sectional route release. Basically, as the back of the train safely clears specific sections of track, the interlocking unlocks them one by one behind the train. It's a super smart way to guarantee safety while allowing maximum capacity on the line.
Finally, Section 6, the fail-safe. Because, let's face it, human beings change their minds and unpredictable things happen.
What if a signaler suddenly realizes they made a mistake and tries to cancel a route that the interlocking already gave a green light for? To prevent a total disaster, the system uses an incredible fail-safe called approach locking. Remember our physics lesson? Trains take forever to stop. If a driver is zooming toward a green light and it suddenly flashes red, they might not physically be able to brake in time. Approach locking is the system's way of respecting that intense physical reality. Here is how it actually works. If a signaler cancels a route, the signal will immediately drop to red to try and stop the train. But the interlocking will absolutely not release the locked route ahead. Instead, an approach locking timer starts. The system essentially says, nope, I'm keeping this track reserved just in case that train can't stop. The route stays completely locked down until the system confirms the train is either safely stopped at the red signal or is far enough away to safely brake. Only then does it release the lock. It really is mind-blowing when you think about the sheer amount of logic running silently in the background of every single train ride. As we wrap up this explainer on railway interlockings, I want to leave you with a quick thought. As high-speed rail keeps pushing the boundaries of physics and our global networks become busier than ever before, how do you think these invisible safety layers are going to evolve next to keep us safe? Definitely something to ponder the next time you're sitting on your commute, protected by the hidden brain of train safety. Thanks for joining me.